Welcome to Talk Tensors. We're back with another deep dive, this time into a really thought-provoking machine learning paper.
Yeah, looking forward to this one.
Today we're tackling, can large reasoning models do analogical reasoning under perceptual uncertainty? So, we hear a lot about models like GPT-4 being great with text. But this paper asks, well, can the newer large reasoning models, or LRMs, handle the kind of messy, fuzzy information our brains process all the time, especially for abstract thinking?
Exactly. It's a critical question. These LRMs, they're showing some real advances in complex problem solving, but mostly in clean textual domains.
Right.
The paper digs into whether they can actually reason when the input isn't perfect text. It's like the difference between solving a neat math problem on paper versus, say, a biologist trying to identify something blurry under a microscope in the field. Totally different game.
Definitely. And to really push these models, the researchers focused on analogical reasoning using Raven's progressive matrices RPMs.
Ah, the RPMs. Classic benchmark.
Yeah, exactly. You might know them as a way to measure fluid intelligence in humans, that ability to solve new problems without just relying on what you already know. It's used for people, and now, increasingly, for AI reasoning tests.
And this paper uses the iRaven dataset, and specifically its tougher sibling, iRavenX.
Okay, tell us about iRavenX. What makes it tougher?
Well, iRavenX really ramps up the complexity compared to the original. You get larger matrices, like 3x10 panels instead of just 3x3 sometimes.
Wow, okay.
And a much wider range of possible features on the objects, attributes, they call them. It forces the models into longer, more complex reasoning chains to figure out the pattern.
But that wasn't the main twist in this paper, was it?
No, the real kicker here is how they introduce what they call perceptual uncertainty into iRavenX. That's the core contribution.
Perceptual uncertainty. Okay, let's break that down. How did they make the problems more, uncertain?
They basically took the nice, clean, symbolic inputs these models usually get.
The ideal data.
Exactly, the ideal stuff. And they roughed it up to make it more like noisy real-world perception. Two main ways they did this. First, they added confounding attributes.
Confounding attributes.
Yeah, think of it like random visual noise or irrelevant details that a real perception system might pick up, but that aren't actually part of the puzzle solution. Like maybe distracting background patterns or colors that don't follow the rule. It just lowers the signal-to-noise ratio.
Okay, so just adding junk information, basically. What was the other method?
They also smoothen the distributions of the relevant attributes. So instead of the model knowing an attribute value with 100% certainty, like this shape is definitely a circle.
A one-hot distribution, as they say.
Right. That's the technical term. Instead of that perfect certainty, the model gets a fuzzier picture. Like it's probably a circle, but maybe there's a small chance it's an oval or slightly distorted. They use things like Gaussian filters or a simpler 3-bin strategy to model this fuzziness.
Kind of like trying to see something clearly on a foggy day.
That's a good analogy, yeah. It mimics that inherent uncertainty in real perception.
So the big question they're asking is, how do the state-of-the-art LRMs, they looked at OpenAI's O3 Mini and the open source DeepSeq R1.
And a distilled version of R1 too.
Right. How do they cope when trying to solve these RPMs under these more realistic, uncertain conditions?
Precisely. And they needed a baseline. So they compared the LRMs against standard LLMs like GPT-4 and Llama 3 on the clean versions of the datasets first.
And they also included a different kind of model.
Yes. Importantly, they also benchmarked a neuro-symbolic model, ARLC, which uses a fundamentally different approach to reasoning, especially under uncertainty.
Okay, got it. So let's dive into the paper structure. What's the core argument they build up front?
Well, they start by, acknowledging the huge strides LLMs have made in generating fluent, relevant text. We've all seen that.
For sure.
But they quickly pivot to the known limitations these models can be brittle when it comes to really complex reasoning and planning, falling short of, say, human abstract reasoning capabilities.
And that's where LRMs are supposed to help.
That's the idea. LRMs are designed to tackle this by scaling up the computation during reasoning at inference time. They explore more possibilities, often using techniques like chain of thought to structure the reasoning process.
Makes sense.
But the paper points out, while LRMs seem promising for text tasks, their ability to handle other modalities, like vision, is much less proven. And this leads straight back to that oracle perception issue you mentioned.
Right, the assumption that the model gets perfect input.
Exactly. They argue that much of the current evaluation work gives these models ideal symbolic transcriptions of visual scenes, totally bypassing the crucial, messy step of actually perceiving and interpreting noisy visual data.
Which is just not realistic.
Not at all for real-world applications. Real perception filters noise, deals with ambiguity, doesn't always have full confidence. So the paper's main thrust is, we need better benchmarks. And that's what they provide with this uncertainty-infused iRavenX. They detail the dataset extensions, the confounding attributes, the attribute smoothing, all aimed at testing reasoning under more realistic conditions, even if it's still in a symbolic setting for now.
Okay. And did they provide some background or historical context for this? Why are RPMs so central here?
Yeah, they do a good job setting the stage. They mention how AI reasoning benchmarks have evolved.
Right.
Early on, it was often logic puzzles, games, things with very defined rules.
And chess or Go.
Right. But Raven's matrices are significant because they come directly from human psychology, designed specifically to measure that core fluid intelligence, independent of language or learned facts. It's about abstract pattern recognition and rule induction.
And this ties into the Oracle perception problem's history.
It does. For decades in AI, especially AI dealing with vision, assuming perfect perception was almost a necessity. Why? Because robust computer vision itself was, and still is, incredibly hard.
Just getting a computer to reliably see was the main challenge for a long time.
Exactly. So if you wanted to test reasoning about visual input, you often had to simplify the seeing part. Give the model clean symbols representing the objects, their properties, etc. This paper really highlights that we're now at a stage where we need to bridge that gap. We need models that can reason despite imperfect perception, not just assuming it away.
It connects to that whole debate about the limits of purely connectionist approaches like LLMs, doesn't it?
Absolutely. Are these giant neural nets enough on their own, or do we need maybe more hybrid neuro-symbolic systems for certain kinds of robust, grounded reasoning? This work feeds right into that discussion.
Okay, so let's get into the experiments. How exactly did they set up the tests for the different models on these uncertainty-filled RPMs?
Right. For the large reasoning models O3 Mini and DeepSeq R1, they use what they call a discriminative setup.
Meaning,
instead of asking the model to generate the missing puzzle piece, they gave it the context panels and then a set of possible answer choices.
multiple choice.
Yeah, essentially multiple choice. Pick the right one. They did this partly to avoid issues where the LRM might find some weird pattern totally unrelated to the RPM rules and generate something plausible sounding but wrong.
Okay.
And they used entangled prompts, feeding all the attribute information together in one go, which they thought might help robustness against those confounders.
Did they use things like chain of thought prompting?
They mention focusing on inference time compute scaling, which is related, but interestingly, they explicitly excluded some common techniques like self-consistency, where you ask the model multiple times and take the majority answer, and providing few-shot examples in the prompt for these main tests.
Okay. And they didn't test on the full data set.
No. Due to cost and compute, they used a random sample of 500 RPM tests from each configuration. Still a decent number, but not the whole thing.
Got it. And what about the neuro-symbolic side, the ARLC model? How was that tested?
The approach there is quite different. It's based on Nessy-Parr neuro-symbolic probabilistic abductive reasoning.
Abductive reasoning. That's like finding the best explanation for observations, right?
Exactly. It's like playing detective. Given the clues, the RPM panels, what's the most likely underlying rule? The key innovation they introduced here was an entropy-based confidence metric built into ARLC.
Entropy-based confidence. How does that work?
Think of it as a smart filter. For each attribute, like shape, size, color, the model tries to figure out the rule. The entry metric measures how confident the model is about the rule it found for that specific attribute. If the confidence is high, low entropy, it's really sure about one rule, that attribute's evidence gets weighted more heavily in the final decision.
Ah, I see.
But if the confidence is low, high entropy, maybe multiple rules seem equally likely, or it's just confused, perhaps due to noise, then that attribute's contribution is down-weighted. It helps the model focus on the reliable signals and ignore the noise, like those confounding attributes.
So it learns to trust the clearer parts of the puzzle more.
Precisely. They integrated this into ARLC and evaluated it on the same uncertainty-infused iRavenX benchmarks.
Okay, the moment of truth. Let's talk results. What did they find? Starting with the LRMs versus the LLMs on the clean data.
Right, the baseline check. First off, they confirmed what others have started showing. These LRMs, like O3 Mini and R1, are generally stronger analogical reasoners than the standard LLMs like GPT-4 or Llama 3, at least on these RPM tasks.
How much stronger?
They achieve comparable or better accuracy, often with less prompt engineering needed. O3 Mini, for instance, did better than GPT-4 with similar prompt complexity. They were especially better on the harder iRavenX problems, the longer reasoning chains, the wider attribute ranges.
Particularly arithmetic rules you mentioned.
Yes, LLMs showed a really significant drop-off on arithmetic progression rules, while the LRMs handled them much better.
Interesting. Any difference between the LRMs themselves?
To some nuances. Overall performance was kind of similar between O3 Mini and R1. O3 Mini seemed slightly better on the original iRaven, while R1 had a slight edge on the more complex iRavenX. The distilled version of R1, unsurprisingly, performed worse than the full model.
Well, there was a catch, right? The computational cost.
Oh, absolutely, a big one. The LRMs, while more accurate, used way more tokens, meaning more computation compared to the LLMs to get those results. That's part of their design, scaling compute at inference time, but it's a trade-off.
Okay, so LRMs are potentially better, but more expensive on clean data. Now, the critical part, what happened when they introduced the perceptual uncertainty?
This is where the story really takes a turn. Both O3 Mini and R1 took a major hit. Their accuracy dropped significantly when dealing with the confounding attributes and the smoothened, fuzzy distributions.
Was one LRM more robust than the other?
There were slight differences. R1 seemed a little more resilient to just the confounding attributes on their own. O3 Mini, conversely, held up slightly better against just the smoothened distributions, specifically the bin smoothing method.
But what about when both types of uncertainty were present? That seems like the most realistic scenario.
Disaster, basically. When they combined confounders and fuzzy distributions, the accuracy for both LRMs just plummeted. It dropped towards random chance, essentially guessing.
Wow. So the combination was brutal.
Really brutal. And interestingly, O3 Mini started using even more tokens under these really uncertain conditions. It seemed like it was trying harder, scaling its computation more, but it wasn't helping the accuracy. R1 didn't show that same increase in token usage under pressure.
So the extra effort didn't translate to better results when the input was noisy.
Not in this setup, no. The big takeaway here is that moving from clean iRavenX to the versions with perceptual uncertainty caused a massive drop in LRM performance, and that uncertainty was clearly the dominant factor.
Okay, stark results for the LRMs. How did the neuro-symbolic contender ARLC fare in this challenging environment?
Complete contrast. ARLC showed remarkable robustness. Its accuracy remained high, even with a large number of those distracting, confounding attributes.
That entropy metric paying off.
It really seems so. It also handled the smoothened, fuzzy attribute distributions much, much better than the LRMs.
So even in the toughest scenarios with combined uncertainty.
Significantly better. Where the LRMs dropped to near random guessing, ARLC maintained strong performance. Its accuracy decline from the clean iRaven dataset to the hardest, noisiest iRavenX setting was only modest. It massively outperformed the LRMs in those conditions.
And could it still learn the rules?
Yeah, they mentioned in the appendix that ARLC could still effectively learn the underlying reasoning rules even during training when the attribute data it saw was highly uncertain.
Okay, so the overall picture seems pretty clear. LRMs are powerful reasoners when the data is clean and symbolic, maybe better than LLMs, but they're very brittle when faced with noise and uncertainty that mimics perception.
That's it in a nutshell.
Whereas these neuro-symbolic approaches, or at least ARLC with its specific mechanisms, seem much better equipped to handle that kind of ambiguity and noise.
Exactly. The paper wraps up by emphasizing this gap. Existing benchmarks often ignore perceptual uncertainty. Their augmented iRavenX helps address this. They show LRMs improve reasoning productivity but fail significantly under simulated perceptual noise.
While NESI models show robustness.
Right. Though they acknowledge NESI models like ARLC might be less flexible or general purpose across all domains compared to the broad potential of LRMs. The final word is that building truly robust, open domain reasoning systems that can handle real-world messiness is still a major hurdle.
Really fascinating findings. Okay, let's shift gears into our novel notions segment. Based on this work, what's a potential future research idea that springs to mind?
Well, one thing that seems like a natural next step, building directly on these findings, is exploring how to integrate explicit uncertainty modeling within the large reasoning models themselves.
Okay, so instead of just giving them fuzzy input, make the model aware of the fuzziness.
Kind of, yeah. Imagine when the LRM processes an attribute, say, the size of an object, its internal representation wouldn't just be the value large, but maybe large tagged with a confidence score, like large confidence 0.7 or something indicating the uncertainty distribution.
How would that help?
Well, it directly addresses the problem highlighted by the paper, right? The LRMs currently treat all input symbols almost equally, even the noisy ones. If the model knew some inputs were less reliable, it could potentially learn to downweight them during its reasoning process. It tries to bridge that gap between probabilistic perception and the often deterministic reasoning chains in current LRMs.
Sounds like it could borrow ideas from other areas.
Definitely. You could look at, say, Bayesian deep learning techniques, which are all about quantifying uncertainty in neural network predictions. Applying similar ideas within the reasoning process of an LRM could be really powerful.
And the potential impact.
You could get LRMs that are inherently more robust to noisy sensor data in robotics, autonomous driving, medical image analysis, any domain where perception isn't perfect. Right now, our prompting methods don't really offer a way for the LRM to explicitly reason about the quality of the input data.
Okay, let's game out some possibilities. High probability scenario.
High probability. Maybe we see new LRM architectures with attention mechanisms that are actually modulated by input uncertainty scores. The model learns to pay more attention to the reliable bits.
Medium probability.
Medium probability. Training data sets get augmented with explicit uncertainty labels for attributes, and fine-tuning LRMs on this data demonstrably improves the robustness to real-world noise.
And a low probability, maybe more speculative idea.
Low probability, but cool to think about. Perhaps LRMs develop some kind of emergent capability to infer input reliability just from the patterns in noisy data without any explicit uncertainty tags needed. That seems less likely near term, but who knows?
Interesting. It feels like a necessary step if these models are going to operate reliably outside clean digital environments.
Absolutely. It's not just about scale. It's about robustness and adaptation.
So what's another angle? A second research idea from this.
Okay, another direction, maybe slightly different, could be exploring adversarial training, but specifically for this symbolic reasoning context.
Adversarial training. Usually we think of that for images, right?
Yeah.
Like adding tiny noise to fool an image classifier.
Exactly. But here, the idea would be to create adversarial examples at the attribute level. You wouldn't tweak pixels. You'd tweak the symbolic descriptions fed to the LRM in ways designed to maximally confuse its reasoning process.
How would that work? Like introducing really sneaky confounders?
Precisely. Or subtly shifting attribute values in ways that exploit weaknesses in the model's rule inference logic. You'd essentially be training the LRM to be more resilient against misleading or slightly incorrect symbolic inputs that mimic perceptual errors or noise.
Why would this be useful?
Well, adversarial training has proven pretty effective at making standard deep learning models more robust in various domains. Applying that philosophy here could directly target the brittleness this paper exposed. If you train an LRM to withstand these crafted symbolic attacks, it might become generally better at filtering out real-world noise or handling slight inaccuracies from a perception module.
Making it less likely to be thrown off by, say, sensor glitches or imperfect object recognition.
Exactly. Right now, LRM training is heavily focused on language modeling and logical reasoning on clean data sets. This adversarial approach would explicitly target robustness to imperfect perception-like symbolic inputs.
Okay, scenarios for this one. High probability.
High probability. Researchers start creating specific data sets featuring these adversarial symbolic perturbations, designed purely to benchmark and improve the reasoning robustness of models like LRMs. Medium probability. Adversarial training against symbolic noise becomes a standard part of the fine-tuning process for LRMs intended for applications involving real-world perception.
And low probability.
Low probability. Maybe through massive scale and diverse enough training data, LRMs just naturally develop a high degree of robustness to these kinds of symbolic perturbations without needing explicit adversarial training targeted at this. Seems less direct, though.
Gotcha. Both ideas seem like really crucial avenues for making these reasoning models more practical. Of course, we should add the usual disclaimer.
Oh, yeah, definitely. This is all speculative, just exploring possibilities based on the paper for entertainment and discussion.
Right. Well, that brings us towards the end of this deep dive. What's the main takeaway for our listeners?
I think the clearest message is this duality. Large reasoning models, impressive potential for complex reasoning if the input is clean, but introduce the kind of uncertainty inherent in real-world perception, even simulated uncertainty, and they currently struggle quite badly.
Well, the neuro-symbolic approach showed surprising strength there.
Exactly. The robustness of ARLC in this paper really highlights that maybe combining neural flexibility with more structured symbolic reasoning, especially mechanisms that handle uncertainty, could be key. It hints towards hybrid architectures.
Definitely food for thought. We hope this discussion prompts you, our listeners, to think about what it truly means for an AI to reason effectively, especially when dealing with the messy, ambiguous reality outside of clean data sets.
It's a huge challenge moving forward.
Indeed. As always, if you want to dig into the details yourself, the link to the paper, "Can Large Reasoning Models Do Analogical Reasoning Under Perceptual Uncertainty?" is available in the description. Thanks for tuning in to Talk Tensors.
Until next time.